Welcome back to this lecture on inference rules. In this fourth and last segment, we will discuss a very important inference rule called resolution. Resolution has two premises, namely P or Q and not P or R. So its premises are two disjunctions, and the critical point here is that it's not just any two disjunctions, but the first disjunction contains a proposition P and the second one must contain its negation. So what can we infer from these two propositions? Well, let's say that we all agree P must either be true or false. And let's assume these two premises are true. Well, if P is true, then therefore not P is false. And since the second premise is true, then R must be true. So if P is true, then R must be true. But of course, P could be false. And if P is false, right here, then Q must be true, since the second or the first premise must be true. So if P is false, then Q must be true. If P is true, then R must be true. So either way, either Q or R must be true. And that's the conclusion of the inference rule called resolution. Now this is just an intuition for why it's a valid form of reasoning, a valid template for reasoning. Make sure you go ahead and prove the validity of this inference rule using a truth table. So the reason you absolutely need to know about resolution is that this inference rule is probably one of the most used in computer science. It's a very powerful rule. In fact, it's the basis for the programming language called Prolog, which is used a lot in AI. And also resolution is at the heart of many theorem provers. So in other words, it has a lot of applications in computer science. And to prove to you or to give you a sense for why this rule is really powerful, I'm going to argue here that this rule is more general than, or it subsumes some of the rules we've seen before. In other words, some of the other inference rules are special cases of this one. For example, remember the inference rule called the disjunctive syllogism. Let's prove that this inference rule is a special case of resolution. Now remember, the premises for the disjunctive syllogism are P or Q and not P. And from that you can infer Q. Well, if you compare this inference rule with this one, you realize there's similarity. The only thing that's missing here is the second operand in the disjunction in the second premise. So how can we change this second premise by adding a disjunction and a second operand without changing the truth value of the premise? Well, we can use the second law of identity and add the disjunction or with any proposition that's always false. In other words, any contradiction. Not P or F, remember, is logically equivalent to not P. And now we match the template for resolution where R is now F. So what can we imply? We can imply Q or R, which in this case would be Q or false. So let's write this down. And again, using the second law of identity, we know that Q or false is logically equivalent to Q. In other words, if you remove what's written in red here, you get the disjunctive syllogism. But when you take it all into consideration, it's nothing but an instance of this template. And we could also prove formally that the disjunctive syllogism is a special case of resolution. And the way we're going to do that is by writing a formal proof starting only with the premises of the syllogism and ending up with the conclusion of the syllogism, namely Q. And to write this proof, we're going to use resolution. The new inference rule that we claim here is more general than the syllogism. So, the next step in the proof, step number 3, will be to infer not P or false by applying the second law of identity to proposition number 2. From there, we can infer Q or false by applying the rule of resolution on propositions 1 and 3. And finally, we can infer the proposition Q by applying again the second rule of identity to proposition number 4, and thereby dropping the disjunction with false. So in conclusion, the disjunctive syllogism is just a special case of resolution. In fact, another well-known inference rule, namely the modus ponens, is also a special case of resolution. Now remember, the premises for the modus ponens are P implies Q and P, from which you can infer the proposition Q. Now it's not so obvious in this case that this modus ponens inference rule is a special case of resolution, because the first premise here is a disjunction, whereas the first premise here is a conditional. But this is where we're going to use our well-known logical equivalence that we called asterisk to convert the conditional to a disjunction. And now we are in familiar territory. We can always rewrite P as P or false, and now we have the form of resolution. Those two premises fit exactly the template for the premises of resolution, therefore we can infer the conclusion of resolution Q or false, which is logically equivalent to Q, which is the conclusion of the modus ponens. I'll let you go ahead and write the proof, the formal proof, to prove that this is indeed the case. I'm going to skip it here on the slide, and I'm going to give you two exercises for you to work on at home. I want to convince you that resolution is indeed a very general rule. So as a third example, I want you to convince yourself that modus tollens is also a special case of resolution, and that the hypothetical syllogism is also a special case of resolution. In other words, this resolution rule is quite powerful, and it's more general than any one of these four inference rules that you already know. And this concludes our lecture on inference rules for propositional logic.